Hi, I'm Mark Barsamian. In this video, we'll finish our discussion of section 5.5, actually finish our discussion of chapter 5, with a discussion of what's called the average value of a function over an interval. This material is from section 5, of course, the fundamental theorem of calculus. It's from the end of that section, pages 375 to 377. Two examples are related to what we're doing in this video. The corresponding homework is this set of 4 exercises from section 5.5. Recall some stuff from previous videos. The relationship between the definite integral and signed area. Remember that the definite integral of a function from a to b, denoted by that symbol, means in terms of the graph, the signed area of the region between the graph of the function and the x-axis on that interval. And recall the relationship between definite integrals and antiderivatives as articulated by the fundamental theorem of calculus. The fundamental theorem of calculus says this definite integral is equal to this calculation involving an indefinite integral. And recall the substitution method that's shown on the next page. The substitution method is this 5-step method that I presented a few videos back. The book has a substitution method that's presented quite a bit differently. So as I said, we will be discussing today the average value of a function over an interval. We'll start with a geometric question. Suppose you have a given function that's continuous on a closed interval. Then there's a number denoted by SA that's the signed area between the graph of the function and the x-axis on that interval. So there is a picture of that region. Now suppose we want to put a rectangle on the same interval, and we want that rectangle to have the same signed area. The question is this: what would the height of this rectangle have to be? We know its width because we're putting it on that same interval. But the question is, what would the height h of this rectangle have to be? So that's our geometric question. Well, the answer to that question is straightforward. For the region between the graph of f and the x-axis, the signed area is, of course, given by this definite integral. So that area, the area of that region, is given by that definite integral. For the rectangle, the signed area is just width times height. The width is the width of the interval, and the height is this unknown letter h. The width is that b minus a, and the height is this unknown letter h. So the area is just the product, b minus a times h. So we want those two things to be equal, the signed area under that graph to be equal to the area of that rectangle, so we just have this equation. Now we can divide both sides of this equation by the quantity b minus a, and we arrive at this formula for the height. The height is given by this expression, the definite integral divided by the quantity b minus a. So we have answered our geometric question. Remember that geometric question was, how high would this rectangle have to be? The answer, that's the height h, is given a name. It's called the average value of f over the interval a comma b. Now, you can talk about this average value when you have a function f that's continuous on an interval a to b. And there's the definition of that expression. The average value of f over the interval ab is this number h given by this integral calculation divided by the quantity b minus a. In this video, we'll consider 3 examples about computing the average value of a function on an interval. Example 1. Find the average value of this function on this interval. Well, let's go review our formula. The average value of a function over an interval is given by this formula. We compute the definite integral, and then we divide by b minus a. So there's our definite integral. And then here in front, we're dividing by b minus a. So the definite integral has as its integrand whatever that function is. That just goes in there. Oh, and there's a typo here. This should say the integral from -3 to 2. So when you set up the calculation, this is the a, and this is the b, and so we need to divide by the quantity b minus a. So we divide by the quantity 2 minus -3. Well, the calculation of h is here. We're just going to do that definite integral. Now, I've simplified the expression in front. That 1 over b minus a is just simply 1 over 5. And then I've used the fundamental theorem of calculus to replace this definite integral with this expression involving the indefinite integral. That's what the fundamental theorem of calculus tells us. And then, using the same kind of organization that I've used for the last couple of videos, I break off this indefinite integral calculation and I put it over on the side. In this indefinite integral details box, I bring the result back and put the result there. Notice there's nothing surprising about this indefinite integral calculation. Here I have a power function with n equals 1. Here I have a power function with n equals 2. So I've used, on the next step, the power rule with n equals 1 and with n equals 2. And remember that whenever you do an indefinite integral, the constant of integration shows up immediately after the integration symbol goes away. So in every step from here on, there's a plus c. Also notice that that whole expression with the constant of integration is the indefinite integral. It's the general antiderivative. It's the function form. And I denote it capital G of x because the original function was denoted little g of x. So we integrated little g of x, and when we integrate little g of x, I denoted the result capital G of x, following the convention that I have been using off and on through chapter 5. So this function form is what goes in those parentheses. From here on out, it's just arithmetic. Notice that the plus c's cancel in the subtraction step, and we have this evaluation notation that we have to do very carefully. We have to substitute in x equals 2 into that general antiderivative form. We have to substitute in x equals 3 into that general antiderivative form, and then we subtract. The result is the number 5. That is the value of h. Question B says, illustrate the result using a graph of g of x. Well, here I've drawn the graph of little g of x. There's the x-axis. There are the places where x equals -3 and x equals 2. I've shaded the region between that graph and the x-axis. I've shaded the regions above the axis in green, kind of like grass on a hillside. I've shaded this region that's below the axis in blue, kind of like water in a lake. Now that signed area is denoted by the definite integral. On the graph below, I've graphed the horizontal line y equals 5. On that same interval from x equals -3 to x equals 2. And the x-axis is here. So I've got this red rectangle sitting on the x-axis. Notice that that rectangle is 5 units wide and 5 units tall. And that 5 units tall is the h that we found. The 5 units of width is the b minus a. So what we found in this problem was this value of h that would make this rectangle down here the correct height to have the same signed area as this graph up there. Let's go on. Example 2. Find the average value of this function, f of x equals 5 squared of x, on this interval, closed interval from 1 to 16. Well, the solution is we again need to find that quantity h. To find h, we find the definite integral of little f of x on the interval from 1 to 16, and we divide by b minus a. That is, we divide by the quantity 16 minus 1. That calculation is on the next page. So here we go. Here's the definite integral set up as on the previous page. I simplified a little bit. In the denominator, I'll have a 15. In the numerator, we have a 5. That simplifies to 1/3. And I wrote the square root of x in power function form in preparation for finding the integral. Then I used the fundamental theorem of calculus to relate this definite integral to this expression involving an indefinite integral. Fundamental theorem of calculus tells us that those two things are equal. Then, following the usual organization, I break off this indefinite integral calculation and I do it over on the side. And when I'm done, I bring the result back in and put it in those parentheses. The indefinite integral calculation is straightforward. We have a power function with n equals 1/2. So I use the power rule for indefinite integrals with n equals 1/2. I then just have to use careful arithmetic. 1/2 plus 1 is 3/2. Dividing by 3/2 is the same as multiplying by 2/3. And of course, immediately after the integration symbol goes away, the constant of integration plus c shows up and remains in every step after that. So the result is this function form. That is our capital F of x. That's what goes back in those parentheses. Notice that the constant of integration gets brought over and disappears in the subtraction step. The rest is just careful arithmetic. There is one slightly tricky step that you all might be rusty on, partly because you've probably been using calculators too much. How do you do a calculation like that? Well, remember that 16 to the 3/2 can be written as 16 raised to the 1/2 times 3 power. And that is equal to 16 to the 1/2 raised to the 3 power. And 16 to the 1/2 is just the number 4, the square root of 16. And then 4 cubed is a number that we can do. That's just 64. So there's an important fact that we use, a rule of exponents. We use that rule of exponents to justify this equal sign. So you'll have a calculation like this in one of your homework problems. You'll have a number raised to a fractional exponent, and the key thing is to scrutinize that number. If you scrutinize that number that's the base of that exponent, in this case it was the 16, you realize that you can do 16 to the 1/2 power, or whatever is in the denominator of that fractional exponent. That denotes finding a root, like a square root. You can do the square root of 16 in a straightforward way. In your homework problem, you'll have a similar kind of expression involving a base whose root you can find. And as I said, the rest of this is just straightforward arithmetic resulting in a value of 14. That is our number h. Question B is to illustrate the result using a graph of little f of x. Well, here I've drawn everything on one graph. I've got a graph of little f of x, which is 5 square root of x. That's this black graph. And the interval that we're interested in is from x equals 1 to x equals 16. And so the region between the graph of little f and the x-axis is this green shaded region. That whole green shaded region. I've also graphed on the same axis the horizontal line y equals 14. And you can see there the red shaded rectangle that sits on the same interval. The width of that rectangle is 15, And the height of that rectangle is the number h that we found, h equals 14. So the area of that red shaded rectangle is the same as the area of that green shaded curvy region. Let's go on. Example 3. A drug is administered to a patient by a pill. The drug concentration in the bloodstream is described by this function. Capital C parentheses T, that is for concentration, is this rational function, valid for this interval from 0 to 24. So T is the time in hours after the pill is taken, and capital C of T is the drug concentration in the bloodstream in milligrams per liter at time T. The question is, find the average drug concentration in the bloodstream over the first 6 hours. Give an exact answer and give a decimal approximation. Well, we need to find this quantity h, which is the definite integral of that function capital C of t over the interval 0 to 6. So that definite integral, and then divided by the quantity b minus a, that is the quantity 6 minus 0. Now we can simplify this a little bit. Because the constant multiple rule, I can pull this 0.6 out front, so we end up with 0.6 over 6. Well, 6 over 6 would be 1, so 0.6 over 6 is just equal to 1 over 10. So the quantity that we are looking for, our h, is given by this integral formula, 1 over 10 times that definite integral. I'll do that calculation on the next page. So here's the calculation that we need to do. The fundamental theorem of calculus tells us that we can replace this definite integral with this calculation involving an indefinite integral. Now the indefinite integral calculations are on the next page. The result of the indefinite integral calculation gets brought back and put in these parentheses. And we'll see on the next page that that indefinite integral ends up giving us this general antiderivative, this function form that involves natural logarithm. 1/2 ln of absolute value of the quantity t squared plus 9 plus capital C. Now that's a bad choice for a constant of integration. Maybe I should have used the letter k, because we've already used the letter capital C in this problem. It's the function that's the concentration. Now, the indefinite integral result gets brought back in and put in these parentheses, and then we go to work. We have to substitute in this t equals 6. We have to substitute in this t equals 0, and subtract. The steps are straightforward. We end up with ln of absolute value of 45 in this expression, and ln of absolute value of 9 in this expression. And this came up in a previous video as well. From here, you've just got to very carefully go step by step and simplify. First of all, notice that absolute value of 45 is just 45, and absolute value of 9 is just 9. So those simplify. And then remember a rule of exponents. A rule of exponents tells us that this ln of 45 minus ln of 9 can just be replaced with ln of 45 over 9. Then, of course, 45 over 9 is just 5. So I end up with this exact answer, 1 over 20 times ln of 5. Remember, the instructions were give an exact answer and a decimal approximation. So you can see how the problem should be done. The problem should be worked out entirely in symbols. And at the very end, the very last step, you type that symbolic expression into a calculator to get a decimal approximation. Keep in mind that the exact answer involves these symbols. The decimal approximation only has 3 digits, but even if I'd written down all 10 digits on my calculator, it would still be an approximation. The only way to write the answer exactly is to use symbols like that. Now here are the indefinite integral details. Remember that after we simplified on the previous page, we had 1/10 times this definite integral And then we use the fundamental theorem of calculus to replace this definite integral with this calculation involving this indefinite integral. So the indefinite integral that we're going to be computing is the indefinite integral of t over the quantity t squared plus 9. Well, that definite integral will involve substitution. The inside function is this t squared plus 9. That's our u. Then, of course, u prime will be 2t. So I end up with this equation that says dt equals 1 over u prime du, or that is dt equals 1 over 2t du. And then I do substitutions. The red circled equation lets us replace the dt with that red circled stuff. The green circled equation lets us replace this t squared plus 9 with that u. So that's my substitute step. And then in the cancel step, I cancel that t. That t in the numerator cancels the t in the denominator. I end up with a 2 in the denominator. That comes out front in my simplification step. Instead of having a 2 in the denominator in the inside, I just have a 1/2 in front. And I don't rewrite this form as u to the negative 1 because I can't use the power rule when n is negative 1. I have to leave that as the indefinite integral of 1 over u. That's how I ended up with ln of absolute value of u. The indefinite integral of 1 over u is ln of absolute value of u. So that's how we ended up with our general antiderivative of this function form involving natural logarithm. Question B is to illustrate the result using a graph of the concentration, capital C. Well, here I've got a graph of the concentration. And the interval is from 0 to 6. Now, in a previous video, we've actually encountered a function like this before in a problem about drug concentration for a drug administered by a pill. Way back in Chapter 4, when we were studying increasing and decreasing functions, we studied a function like this, and we found the interval where the function was increasing and the intervals where the function was decreasing, and we noticed that there was a critical point at that peak. So in the current problem, we're doing this very different thing. We're considering the area under that graph, or the area of the region between the graph and the x-axis. So also plotted here is this horizontal line, whose height is that value h, 1/20th of ln 5. That was the value of our h. You can see that it's believable that that green shaded region between the graph and the t-axis from t equals 0 to t equals 6 looks like it could be the same as the area of that red shaded rectangle. So the height of this rectangle is that h that we found. And of course, the width of the rectangle is this number 6. That's the end of that example. That's the end of the video, and that's the end of our discussion of Chapter 5.